Hello everyone, this is Samir Abu Haidar speaking. I am a PhD researcher in robotics and artificial intelligence at Mines Paris PSL and COALIST, and today I'll be presenting to you HARP-NeXt, a high-speed and accurate range point fusion network for 3D LiDAR semantic segmentation. Semantic analysis of 3D point clouds that are typically generated by LiDARs is crucial to numerous applications for mobile, autonomous, and robotic systems, such as object detection and recognition, tracking, and scene reconstruction. Such systems often rely on embedded computing architectures as their core computational components because they are lightweight, compact in size, and energy efficient. However, they are also resource constrained. Additionally, as safety is top priority in such systems, it is required that 3D perception models achieve both high segmentation accuracy and low latency. However, existing state-of-the-art 3D semantic segmentation methods were not designed nor tailored for deployment on embedded systems. Therefore, we propose HARP-NeXt, a lightweight network that is designed for fast and reliable 3D scene understanding. HARP-NeXt initially projects the input point cloud into 2D range images and leverages both 2D representations and raw 3D points, making it a fusion-based network. Its architecture is also composed of three main components: the features encoder that embeds initial per point and per pixel features, the backbone that hierarchically extracts and fuses pixel and point features from multiple scales that enhance the network's learning capability, and finally the fusion head that fuses multi-scale features from both 2D and 3D representations prior to the network prediction. In the pre-processing phase of HARP-NeXt, the 2D range images are obtained by applying a spherical projection of the point cloud that converts each point through a mapping from 3D to 2D into image coordinates. In order to accelerate this process, we propose a novel preprocessing workflow. In contrast to the classical preprocessing pipeline that entirely preprocesses the data onto the CPU in the CPU and prepares the neural network inputs in the CPU and later moves them to the GPU only for the inference, our preprocessing workflow immediately moves the raw data to the GPU and preprocesses the data on the GPU, leveraging the hyperrealization of the GPU cores. This reduces the CPU load and minimizes the data transfer bottlenecks that will raise the efficiency in the preprocessing phase. Additionally, we propose a novel conv-SE-NeXt module, a feature extraction block that effectively captures patterns without relying on deep layer stacking. This will reduce the computational cost in the inference part of the network. Our design is inspired by ResNet, SE-ResNet, and conv-NeXt blocks. It incorporates depth-wise separable convolutions that largely reduce the number of parameters in the network. It also integrates a squeeze and excitation mechanism that is designed to adaptively recalibrate feature responses, acting as an attention mechanism that focuses on the most informative features. In HARP-NeXt backbone, we fuse both pixel and point representation hierarchically throughout the network stages, and in each stage we employ a single conv-SE-NeXt module acting as a standalone feature extractor without the need of deep layer stacking per network stage. This will make HARP-NeXt a lightweight and shallow network that is highly efficient. Additionally, the point features are used to refine the pixel features in a multi-scale manner, meaning the point features from the previous stage are mapped to pixel features that are later fused in the next stage with the extracted pixel features from conv-SE-NeXt in a residual attentive manner. This process is repeated in the 4 stages of the network. Finally, we stack and aggregate the output of each stage on both pixel and point level and aggregate them to later fuse them in the fusion head before the final predictions of the semantic labels. As we report the accuracy in terms of mean intersection over union versus the total runtime that includes both the preprocessing and inference time, we observe on new scenes that HARP-NeXt achieves high accuracy in real time, that is the green zone, with fast execution on the RTX 4090 GPU. HARP-NeXt breaks the performance trend observed by state-of-the-art methods. Similarly, on the NVIDIA Jetson AGX Orin embedded system, HARP-NeXt is the only highly accurate method to run and be executed in near real time. A similar trend is also observed on Semanticity benchmark, further validating the high efficiency and accuracy of HARP-NeXt. Thank you very much for your attention.